And so I want to talk today about kind of what AlphaFold models, and I'm using AlphaFold to represent all the advanced AI methods, what they're good for, and what you have to pay attention to when you're using them. And then I'll show you how you can use them in your structure determination pathway. So let's talk about AlphaFold models a little bit. So this is a picture of a small piece of an AlphaFold model superimposed on a density map. This AlphaFold model is just taken right from the prediction, just like superimposed, and it's awesome, right? This is spot on. It looks exactly like, not exactly, but extremely much like the density map that came from a different place, right? So this AlphaFold, part of this AlphaFold model is really, really great. This has a very high confidence, and I'll talk about confidence measures for AlphaFold in a moment. So this prediction was predicted with high confidence, and in fact is very good. Here's one that actually is predicted with the same confidence as this one, but it's actually not right in this region. And as we'll see in a moment, this is less common than that situation, but does occur. And another fairly common, oh, there it is, situation is that the AlphaFold model is actually very similar to the structure you might find, but it's just a little bit distorted. So you see in this picture that the helix on the right is just shifted a little bit by a couple of angstroms. The whole thing is distorted, but if you just translated it a little bit, it would superimpose on that density very well. So these are kind of three very common situations. And AlphaFold not only predicts a structure, but for each residue, it produces a residue-specific confidence measure, PLDDT for short. It basically helps you identify where errors are more likely in the prediction. And let's talk about that prediction confidence a little bit. So we basically took a bunch of structures and analyzed the relationship between PLDDT and RMS error. So the PLDDT, the AlphaFold creators weren't quite so interested in RMS errors because they use different measures to compare structures. But in cryo-imaging crystallography, a lot of the time we want to know basically how far off is it. So here we've kind of translated the results into RMS errors. So PLDDT bigger than 90 is generally thought of as very high confidence prediction. So like we really think we know what it is. And so we analyzed a bunch of structures with that high confidence, and the median prediction error for after superimposing a structure, an AlphaFold model on the corresponding deposited model, the median difference between those after superimposing them is 0.6 angstroms. So half of the residues, C alpha positions of half of the residues are within 0.6 angstroms, which is very good. And the other half was not, and 10% were like quite a ways off, like 2 angstroms off. So what this means is, sort of on average, not for any particular structure, about 10% of the residues in predictions are going to be quite a ways off, but a good part are going to be very close, like 0.5 or 0.6 angstroms. Now, if you have a lower confidence in prediction, it kind of goes up correspondingly. So if you have 80 to 90 for this, and this is considered high confidence, then it's basically double, 1 angstrom median and 20% or over 2 angstroms. If you go to moderate confidence, 70 to 80, then once again, another factor. So 1.5 angstroms median and 30% of them are more than 2. Once you go down to relatively lower confidence, under 70, it's quite a bit worse. Now, much of AlphaFold models are in the high confidence range. So actually, a lot of the time you're good. And remember, a good part of this, a useful part of this is that for each individual residue in your prediction, you get a number. And so you can say these residues have very high confidence, and most of them are going to be right. Almost all of them are going to be right. And these residues have low confidence, and most of those are not going to be real close. Okay. So here's an example, kind of putting that into real terms. Here's a small structure that's a dimer, and I've color-coded the residues by PLDT confidence over 90 are the blue ones, and the green ones are 80 to 90. So over 90, very high confidence, 80 to 90, high confidence. And what do we expect? We expect the blue ones then are going to be kind of within about half angstrom, half the time, and the green ones maybe 1 angstrom off. And you can kind of look at these things and see what part of my molecule am I more confident about, which part am I less confident about. Another aspect of confidence that AlphaFold provides us that's also very useful is the predicted aligned error matrix, or PAE matrix. This is a matrix that says if I look at one, if I superimpose my structure and the true model, which I don't know, using around one residue, and then I look at another residue, how far off do I think that's going to be? So this kind of tells you a confidence measure for how accurately the relationship of one part of the molecule is to another part of the molecule that can be far away. This can be used by you and by our software to identify accurately predicted domains. So here's an example here of how you can do that. So the x-axis is one residue in which we're going to superimpose in the thought experiment. And then the y-axis is the residue that we're going to ask, how far off do we think this is going to be? And the dark blue here are residue pairs where the uncertainty in position is less than 5 angstroms, so fairly good. And the light blue is where it's more than that. So the upper left corner there, all residues in that range, so everything from 1 to 200 for residue 1, and everything from 1 to 200 in residue 2, all those residues have relationships between them that are known confidently within about 5 angstroms. So that's pretty good. In contrast, and that corresponds to that domain, one domain. In contrast, if we look at the those are 2 domains. If we look at the upper right corner there, that corresponds to the relationship between domains. Residues 200 to 400 for residue I, and residue 1 to 200 for residue J. So that's the between the domains. And we see that in that case, the confidence, most of the residues do not have high confidence for the residues being accurately positioned within 5 angstroms. So that says within a domain, we kind of know the relationship between residues within 5 angstroms. Between domains, we don't. And what does that mean? Or why is that? Well, that's just because the domains are kind of fixed, each one, and they're going to be accurately predicted within the domain. But the relationship between the domains is not well known, and therefore doesn't have high confidence for the relationship between residues that are in different domains. So that tells you what parts of this molecule are probably going to be right with respect to each other, and which ones you would need to split into pieces if you want to try to have accurate domains. So this is a great aid in identifying domains. Okay, so another concept is that AlphaFold can use a model as a template to improve prediction. So normally, the way you get an AlphaFold model is you just put in a sequence, run AlphaFold. It uses all the information from all those structures that are have already been solved, and all the sequence relationships of sequences that are like your sequence to construct a prediction for your model. Now, one of the key aspects of that prediction is the multiple sequence alignment, your sequence, all related sequence, identifying residues that covary. Don't have to worry about the details, but that gives AlphaFold information about relationships between residues in the sequence. If you have a model, like from an experiment, that also can tell AlphaFold something about, to get a head start in what residues are close to each other, what residues are far from each other. So you can supply a model as a template to AlphaFold, not to like use it as this is the answer, but basically tells AlphaFold, this is a good guess for what some things might, for some relationships in this structure. So you can feed in a template. And if you have, in this case, here's an AlphaFold prediction of a model that we won't actually use in this example today, but one of the ones we have in our tutorials. The green is an AlphaFold prediction. And then maybe with experimental data, you can rebuild that model to get the working model, the next one. And then if you use that working model as a template, you can generate a new prediction. And the reason this might be useful is because the new prediction might be better than both the working model that you created and better than the AlphaFold prediction before, because it's combining information from the original prediction with experimental information, so you might be able to get a better prediction after that. So you could imagine that you could cycle this prediction, improve with your experiment, do a new prediction, iterate the whole procedure. So that's something that's available in a Phoenix, and conceptually you could do it anywhere. So here's a specific example of doing that. So here the AlphaFold model is in green, and red and pink is the solved structure, deposited model. And the AlphaFold prediction in one part of it is not that good. Another part of it is fairly accurate. The density map is pretty good. On the left side is where the AlphaFold model was accurate. And then on the right side is where the AlphaFold model wasn't accurate, but actually there's pretty good density there. And so you can rebuild that model, use that as a template, get a new AlphaFold model, which isn't exactly right, but it's better than it was before. And then this one you can see it just needs to be adjusted a little bit. And then use that next one as a template, again, iterate that process a few times. And then finally you have an AlphaFold model that's actually very similar to the deposit model. So, and this last AlphaFold model is just a prediction using a template and using the sequence file again. And now that model without any refinement or anything actually is, in this case, is very similar. Doesn't always work so nicely as this, but the process of iteration does help. Okay, I'm going to skip the X-ray version, which is very similar to that. So what should our strategy be now for solving a structure, given that we have access to AlphaFold models? So we can create an AlphaFold model for any sequence that we have. We can download an AlphaFold model for sequences that somebody else has already run through AlphaFold. We can create AlphaFold predictions for complexes, which may be sometimes useful too. So what's a good strategy for doing all this? So I say, before you do any work, like experimental work, predict your structure with one or more methods. Like I'm talking about when you're thinking about what to do, like you're designing your experiment at the very beginning. I'm interested in this molecule, and I'm interested in, how this thing, what ligands this thing is going to bind to, and how it might operate, and what kind of protein it might be. Well, before you do anything else, you're going to do a literature search and see what everybody else knows about it. If they don't know anything, you're going to do a prediction because it's really easy, right? And that prediction may tell you the answer to all your questions, in which case you're done. You don't have to do any experiments, right? That's actually very rare, so that doesn't happen very often. But I'm just saying that so that you think in terms of the prediction is a very easy thing to do, and it was going to generate a lot of information for you that's going to help you design your experiment, whatever it is. So the experiment then becomes, what experimental things do I want to do in order to increase the amount of information I'm getting from this structure, right? And so, for example, let's say you do an AlphaFold prediction, and the whole thing is predicted with very low confidence. Well, actually, that's going to tell you a number of things. That'll tell you, one, well, that prediction is not telling me much in terms of what the structure is. But actually, if you have a structure and it's almost all predicted with low confidence, that's going to be like a warning flag to you as well, because chances are that structure is either has a lot of disorder in it, or it doesn't look like anything you've seen before. So this is going to be a very challenging problem. So actually you learn that kind of off the top if something is basically unlike anything that's been seen before. But more commonly, you'll see that some parts of your molecule are very high, predicted with very high confidence. And in fact, you might also see that looks just like some other molecule that you've seen before, and you learn things automatically from that. And then you're going to ask, what do I need to learn in addition? And if you want to solve the structure of this molecule, you might, for example, cut off parts of the molecule that are predicted with low confidence, because those often are less ordered. So a common technique in both cryo and X-ray, right, is to trim off all the things that are disordered, so that you get so that in X-ray it can crystallize better, and cryo doesn't aggregate so much. So the predictions of where the domains are help you do that. So lots of things like that you can do. You can design your experimental approach based on your predictions. So think of it in those terms. It's a very useful tool right at the top. And with keeping in mind that the AlphaFold predictions, even those that are very high confidence, aren't always right, but generally they're right? So they're a great hypothesis. They're a great starting point. Okay, so how are you going to do this? So predict your structure before you do it. Design your experiment based on what information you have now. Okay, solve the structure, and I'll show you ways to do that. And using your trimmed, probably predicted model as part of that process. And then you can do this iterative process I just described, update your prediction with your model that you've got. So running AlphaFold with your best model as a template, improve that structure, and you can iterate that whole process as many times as you want. And we have tools, predict and build, for example, that will do that all those things for you automatically. Okay, so what tools do we have that will help you do these things? So we have a tool that will run AlphaFold for you. Of course, you can use any AlphaFold models for this process that I described. But the part of feeding in a template and redoing the prediction is very conveniently done with our server. And all this can be done with our servers also. But our server only runs on single chains. It doesn't do complexes. So if you want to do a complex, do the complex prediction to start off with somewhere else, and then use that as your starting point. So you can feed in a model that's predicted some other way into our tools as well. Okay, so we have a tool in the Phoenix GUI, and we'll do this in a few minutes, that will predict the structure for you very easily. And you can use a template to guide that prediction. You just load in the template along with the sequence file. It does it for you. Just a small comment, a little technical comment, that if you supply a template, then you don't have to use a multiple sequence alignment procedure, because the relationship between residues is supplied by that template, and so it doesn't need the multiple sequence alignment to do it. It sometimes is useful to not include that MSA. You can also use the MSA. You can do it either way. And one other thing, just keep file in the back of your mind. Don't use an AlphaFold model as a template. And why not? It's because it's totally useless. Because if you feed in an AlphaFold model as a template, AlphaFold will say, this is great, because it made it, right? And so it satisfies all of its criteria and says, this is the best model I've ever seen. And then it will feed you back a model that looks like the template. And it'll have very high confidence for the whole thing. It's like, yes, this is just totally perfect, right? So it's that circular process doesn't work. But if you take an AlphaFold model and rebuild it and do stuff with it, that's okay to feed in. But just don't take, it's just useless to be circular with an AlphaFold model. And we use tools, the AlphaFold software, tools from Colab, Fold, MMSeeks, that have been very helpful to us to make all this possible. Okay, we have another tool that will do the trimming of models for you. So you run AlphaFold or another procedure like that. And another small technical thing that's, if you're actually running this, it's helpful to know. When you run AlphaFold, it does a prediction, and it uses one of the fields in the PDB format or MMSIF format to write in where what the confidence level is, the PLDDT. So there's a B factor field or a atomic displacement factor field in these files. And so instead of writing in a B factor, it writes in PLDDT. So it's useful to be aware of this, partly because the PLDDT goes up when the B factor would go down. So you can't use them for each other. But there is kind of a relationship between a B value that's appropriate and a PLDT value. And so this program will basically swap PLDT value for a B value that's somewhat corresponding to it. And it will trim the low confidence parts of the model, and it will identify domains for you. So it does all that very quickly and very easily. So basically you end up with, after running process predicted model, compact high confidence regions from a structure that may be suitable for molecular replacement or for docking in cryo-EM. Okay, so what would be a flow for solving a structure with X-ray and with cryo-EM using the tools now? So for X-ray, you have a sequence file and you have an X-ray intensity data. So you've already collected your data. And so you have like an MTZ file or something like that, and a sequence file, and then what next? Okay, so each one of those can go somewhere. Your sequence file, you can predict the structure, trim and identify the domains, and that gives you high confidence predicted domains that go with your structure. You know, they aren't necessarily right, but they're going to be a good starting point. And then from your data, with your data, then you can do molecular placement, as we'll see later today. And then if your molecular placement is successful, now you have a working structure and a map. And you can carry out density modification to improve that map. You can do auto building or manual building, rebuilding to improve your model. And now you have a rebuilt model and an optimized map. And you can then do another round of prediction of structure starting from that rebuilt model. So now maybe you can get a better prediction. And so you've updated your predictions and you can recycle through this whole process as many times as you want. So you can do this by hand, like one thing at a time, or you can use the automated tools to do the same thing. So for cryo-EM, you have half maps and maybe a processed full map and a sequence file. So instead of X-ray data, you get cryo-EM. And then those half maps, you can put them together with density modification to improve the quality of, to generate a full map that's improved, or you can just do sharpening on that map to optimize the scale factor as a function of resolution to get an optimized map. Your sequence file, just the same as the other one, predict the structure, get domains, you have domains, and then now you have an optimized map and domains. So now you're going to dock them, and we'll see about docking shortly in our tutorials. So now you have docked domains into an optimized map, and you can do the same kind of processes in X-ray. Our standard process is very slightly different. So we have docked domains, and then we can take the full structure without trimming and superimpose that on the docked domains with a little morphing so that if the full structure doesn't necessarily have the same relationship between domains as the domains do when you dock them. So we're going to morph the full structure onto it and then rebuild that. And then once again, you get a rebuilt model, repredict, and iterate the same process. So what are the input and outputs? This one we did. Here we go. The inputs then are experimental data and what's in the asymmetric unit or what's in the cryo-EM map, a sequence file. You can also supply as input any other models that you already have. So like you have a prediction from somewhere else, you can put that in. If you think you know kind of almost the whole answer, you can put that structure in too as kind of a starting point. And the output from this then is a rebuilt model, optimized map, and docked predicted models. And the rebuilt model is ready for whatever next steps you're going to do in structure determination. And the docked predicted models are often useful as kind of a high quality reference model. And we may talk about that in the refinement section. But basically, since AlphaFold models, the high confidence parts of AlphaFold models are often quite accurate. They're often useful as a reference when you're doing refinement. Okay, and so here are all the tools we have. Predict model, we saw process predict model, that's the one that gets the domains. And then for cryo-EM, we have tools for map improvement, for docking, morphing, and refinement. And for X-ray, we have standard X-ray tools for going on once we got to this stage. And predict and build does all these things as a fully automated way. Okay, and I want to thank all the Phoenix team, and we can take a few questions, I think. We have some time. Okay, thanks.